Nice to see you here. So I'm gonna share my screen as usual. And today we'll be working on the first question, which is middle of the linked list. Okay. Can everybody see and hear me?
Yeah.
Okay. Right, so for the first half an hour, we will just figure this question out. I know that a lot of people have no experience with linked lists, so I'm just going to give a brief explanation as to what linked lists are. So linked list is a data structure, right? Like array is also a data structure, but array is a data structure that we are familiar with, right? So for array, we can record different values inside an array, and we can get the size of it. We can traverse the array by using its index, right? But for linked lists, there is no such function for you to traverse it using index, and you cannot know the size as well. So for linked list, it is actually made out of different nodes. So there are different nodes, and for each node, as you can see up here in the definition given, so I'm using C++, but it's almost similar for different languages. So for each node, okay, this is a singly linked list, meaning that for each node, you will get the pointer to the next node, and that's it. So usually for linked list, it would be singly, but sometimes if it's doubly, then you will get the pointer for the previous node as well. So in this case, I have a node, and at each node, I have the pointer to the next node, and I have also the value of the node, right? So if this is an array, then maybe I can then this would be like a linked list. So in a linked list, so in a linked list, I will start with the head. So here the head is 1, and I can go to 2, 3, and 4 by accessing its next pointer. So for 1, so this one, I access its next pointer, and I know the next node is 2. And for 2, I can access its next pointer to know the next node is 3. And for 3, I can access its next pointer to know the next node is 4. And the next node of 4 is null because it's already the end of the linked list. So looking at this linked list, we don't actually know the length of the linked list given just the first node. So in this question, I am given the head of a singly linked list, right? And I need to return the middle node of the linked list, right? So given, we can look at example 1 and example 2. Okay, so if it has odd numbers of nodes, right, then we would have to return the exactly middle one, the absolute middle one. So in this case, in 1, 2, 3, 4, 5, the middle one is 3. In example 2, so if it has an even number of nodes, right, then we would return the one that is larger. So the middle would be in the middle of 3 and 4, right? So we just return 4. Right. Anyone has any questions with the prompt? I think that this wouldn't be very hard to understand. If you're okay, maybe you can just type okay in the chat. Okay, cool. So with this in mind, so usually if this is an array, what we do is we can just get the size and then we divide by 2 and then we just get the middle index and we can access it, right? So anyone has any idea what we can use with this? There are 2 ways of using it. There are 2 ways of solving this actually, yeah. Okay, using 2 pointers. Someone is typing. Let me know if my voice is too soft. All right, go through the linked list to know number of nodes and find the middle one. Okay. Anyone else has any ideas? Okay, someone else is typing. So these 2 are very good approaches. Okay, so I would explain the two pointers approach last. Right, the slow and fast pointer, correct. So I will explain that last. So first we can look through, okay, so there are actually three ways if we count polar ears solution. Okay, so one of the solution is we can traverse the whole linked list, and upon traversing the whole linked list, we can record them in an array, and then we can just access the middle index, right? So okay, I know some of you guys don't know what complexities are, because I know that y'all haven't taken the data structures course, right? But for those who know, right, for those who know, if we were to traverse the whole thing and we put it each in an array, okay, so let me just comment this out. Okay, so the first way is to traverse the whole linked list and record them in an array, right? And then we can just return the array at size divided by 2, right? So array dot size divided by 2. Okay, so for this first approach, the time complexity would be O of n, right? Assuming that there are n elements in the linked list. O of n meaning that we are traversing through the linked list once. Okay? Here, we would also have a space complexity of O of n because we are creating additional array space that is the size of n. Right, so for this approach, the time complexity and the space complexity will be O of n. Oh. Okay, the second one is as mentioned by polar bear. Right, for the odd number of nodes, won't this return third node? You mean like for the first approach? So okay, for example, if it's 1, 2, 3, 4, 5, right? So I already put it in an array, okay? So 5 divided by 2 is 2.5, right? So size is 5. And then 5 divided by 2 is 2.5, right? And since here, this is an integer, okay? Oh no, sorry, you meant for even number, is it? Let me see again the comment. Oh, odd number, right? So for odd number, so it's 2.5, right? But here, since I didn't change it into double, so it would truncate to 2. Okay, and index 2, 0. So index 0 is 1, index 1 is 2, and index 2 is 3. The value of index 2 is 3. So we would still return the desired node, right? Because we must remember that array are 0 indexed. Okay, they start with 0. The indexes start with 0, right? So this is how the first approach works. Okay, the second approach is, as what Polar 8 here has mentioned, we can traverse the whole array. The whole linked list. Okay, and then I would record the number of nodes. Then I would just traverse it again. To get the middle node, right? So this works too. So traversing the whole linked list would give me a time complexity of O of n, right? Okay. And when I traverse it again to get the middle node, so I'm actually traversing it O of n divided by 2, right? Because I'm only going until the middle one, and then I can just return it, right? So technically, the time and space complexity would be better than the first approach. Okay, so the time complexity for this one would be O of n. And since in this approach, we are not using any additional data structures, right? We are not creating any arrays or anything else. So the space complexity would actually be O of 1. Okay. So this is definitely a better approach than the first one. However, today, we are actually going to focus on the third approach, which is the most optimal approach that Marcus and Proton has mentioned. So we can use a slow and fast pointer. Slow and fast pointer. Okay, so what does this actually mean? Maybe I can draw on the Jamboard to show you, right? So for example, if somebody run twice as fast as me, right? So if this is me and this is my friend, okay, we will call him Q. So if I run 2 steps per minute, let's say, okay, and if my friend runs 4 steps per minute, right? Then at the 2-minute mark, I would have ran for 4 steps, and my friend would have ran for 8 steps, right? So you see 4 is actually the middle of 8. So what I'm trying to say is that we can use 2 pointers, okay? One that is going much slower than the other. So the one that is traversing quicker, when it reaches the end, the other one would reach the middle, right? So how do we do this? One, we would move by 1 node each. Okay, this is the first pointer. And the second pointer, we can move by 2 nodes each time. Right, so in this case, at any point, the first node would always be in the middle of the second node. No. The first node would always be half of the length of the second node. Okay, so anyone has any questions until now? This is just the conceptual part of the algorithm, the solution. So are we using a slow and fast pointer, right? So the slow pointer would move 1 step each time, whereas the fast pointer would move 2 steps each time. Okay, so we can actually, run some test cases to make sure. So let's run in this 1, 2, 3, 4. Okay, so I have 2 pointers. Okay, so the first one is the slow one, and the second one is the fast one, right? So for the slow one, I would be moving it by 1 index. The fast one, I will be moving it by 2 index. Okay, so now the slow one is at 1, the fast one is at 2. Next, okay, I'll answer your question later. So next, the slow one would go by 1 step again, and the fast one will go by 2 steps, right? So the slow one is at 2, the fast one is at 4. The slow one will move by 1 step, the fast one will move by 2 steps. However, it has already reached the end. So we would return the node that the slow pointer is pointing at. So the solution would be 3 in this case. Okay, this works for odd numbers as well. So we can quickly do this. Okay, so the slow one will go 1 step, the fast one will go 2 steps, the slow one will go 1 step, the fast one will go 2 steps, the slow one will go 1 step, the fast one will go 2 steps, and it would reach the end of the array. So I would just return 3. So this is the basic logic behind our approach. Okay, somebody asked if there are 2 nodes, what would be the answer? So again, if we read the prompt, it says that if there are 2 middle nodes, return the second middle one. So with if you look at the test case for example 2, 1, 2, 3, 4, 5, 6, we would actually return 4, right? So meaning that if there's an even number of nodes, we would calculate the middle point, which is in the middle of 2 nodes, and we will return the one that is behind. So at 1, 2, 3, 4, I will return 3. So if there's only 2 nodes, then naturally I will return 2. Okay? Does that make sense to you? Okay, if yes, okay, good. So if there's no more questions, we can start implementing the code. So any questions until now? I believe that everyone should be all right with this. Okay, no questions. So I'm going to continue then. Okay, so I also want to introduce another concept. So this slow and fast pointer, right? Some people call it slow and fast pointer, but I like to call them walker and runner. So one person walks and the other one runs, right? So it's called walker and runner. For me, I like to call it walker and runner. So next time if you hear me say runner, I'm referring to the fast node, fast pointer. And if I'm saying walker, then I'm referring to the slow pointer. Okay. I also want to introduce another concept called dummy node. Okay. So what is a dummy node? A dummy node is essentially a node that has no value, and it records the next it records a node at its next pointer. Okay, so for example, in this question, right, so what do I have to return actually? Oh, I have to return the middle node. So in this case, a dummy node is not needed, right? But I think I still want to let you know what this is. So for example, if there is a linked list question, right? And in this linked list question, if it wants you to do some sort of operation in the middle or at the end of the linked list, so you would essentially move the head, right? However, if the question wants you to return the head, but you already moved it, then you cannot return the head back. So what you can do is you can record it in the dummy node. I believe that the next person would tell you more about dummy node, so I would just stop right there and start coding. Okay, so here, first, let's create 2 nodes. Okay, so here I'm just gonna create my walker and runner. Okay. Okay, walker and runner. Yeah, and I will initialize them. So here I can initialize them to the head that is given, and I can check for the next value, right? So for example, if this is head, this is head. Okay, so remember that we will end when the fast node, which is the runner. So we will end when the runner exceeds the linked list. So if it reaches the end, right? So if it reaches the end, it will be a null value. Okay, so while runner is not equal to null and runner.next is not equal to null. Okay, because for runner, we are moving it 2 steps. So we have to check whether the current one and the next one. Okay. So while this happens, I would move the slow node, which is my walker, by 1 node, right? So walker would equal to walker pointing to the next. So here I'm just setting it to be its next node. Okay. And I will be setting the runner to its next two nodes. So next, and then I have to next again. Okay. And at the end, I will return the slow node, okay, which is the walker. So this would conclude our solution. I think I forgot to talk about the complexities, but basically it's just same as the second approach. So it's O of n of time complexity because we are only traversing the linked list once. Technically, right, the third approach should be faster than the second approach by a bit because the third approach is actually O of n plus n divided by 2, but we can simplify it to O of n because it doesn't really matter. So you can look at it as the same complexities, but if you want to be really particular with it, the third one would be the fastest. Yeah. But I think that this is not important. Okay, let me see. Oh, okay. So, right. So for this third approach, my bad, I forgot about something. So since here I'm using 2 pointers, right? So one pointer is moving for O of n. The second one is moving by its half. So it's actually n plus n divided by 2 as well. So we would just change it to O of n. So let me just run this code. Okay. Yeah. So this works. Okay, I'm sorry about this issue, I know, this mistake that I had earlier, because I forgot to consider the slow pointer. So the slow pointer is actually moving for half of the nodes, whereas the fast pointer is moving through all of the nodes. So it's actually n plus n divided by 2 as well. Okay, sorry for the confusion there. Okay, anyone has any questions? The slow and fast. Oh, that was for just now, right? Yeah, okay. So I think I cleared this up. Anyone still confused? Okay. Yeah, so this is the question that we did today. It's not very difficult. Maybe like for this one, don't do the mistake that I did just now, right? Okay, so for the second one, you can just, okay, so for the second one, you would need a dummy node because when you traverse the whole linked list, your head would be at the end and you need to traverse it again from the start, right? So you can save the head in a dummy node and then you can traverse it again until you get to the middle node. All right. Okay, so that's it from my side. I think that we can move to the next question.
Yeah, okay.
Let me just stop sharing my screen.
Voice is okay, right? Like, wait. Okay. So I'm going to share the second question. Let me just pick a Chrome tab. I'll just share my entire screen. Okay. So basically the second question is also a linked list question. It's middle of the linked list. Sorry. It's remove duplicates. Okay, I'll remove our solution first. So basically this question, it's also about linked list. So it's actually very simple to understand. Like Mason just told you, linked list is actually just array. Like it's actually, you can treat it like an array but um, like whether the if you have like questions why we want to use linked list instead of like normal arrays, and that's a question for another session. But today we're going to solve these questions where it says that there are a few properties to this special linked list. It tells us that the linked list is sorted. So our input, so we can safely assume that our input will always be in ascending order. It will always be 0, 1, 2, 3 or 0, 1, 2, 3, 4. There won't be any cases where we are receiving input like this. Okay. So this is an invalid input, and we can assume that this won't happen because the constraint, it says that the list is guaranteed to be sorted in ascending order. So we'll only have input something like this which is sorted, and we know there are a few constraints here. So first of all is that the number of nodes is in the list is in the range of 0 to 3. They will only will have like maximum of 300 300 elements. Okay, like until the maximum is until 300 only there only be a maximum of 300 elements. Then we also know the value of the nodes. It will be in the range of -100. It says node dot value. Okay, until 100 inclusive both of them are. So this looks not so important, but I'll let you know there are some ways that you try to solve this problem. The negative actually becomes quite important. But today we're going to solve this in a. It's actually this is also a very pretty simple question. It depends on the solution. You can have some solution that is very difficult, but the solution that I'm going to introduce today is actually pretty simple. So if we were to look at this, so for those, but if you're not really familiar with linked list and how linked list works, let's just treat it as an array. So let's just think about it. So if we have like an array like this, so let's say 1, 1, 2, okay. So we have an array like this. How are we going to delete this? Delete the duplicates. So there are a few ways that we can do because it's an array. In Python, if you are going to use Python, we can convert this array into a set, which set will ensure that there's no duplicates. Then we convert it back to an array, then it will become an array of 1 and 2. So this is one way but this doesn't really involves a lot algorithm stuff. It's actually pretty simple to be done. This is one way if we were to do it in a normal array way, but this cannot be done in linked list because we cannot convert. It's not to say we cannot, we can, but it's not efficient. If we were to look through the whole linked list and then create a set and convert it back to a linked list, it wouldn't be efficient. So that's not what we're going to do. So let's see if we were to do it in an array way, what kind of way that we still have to remove duplicates. So we can have another solution. So let's just put this here, but I'll just say it's invalid for linked list. Invalid for linked list. So we have another solution. So another solution is that we can loop through the array. Okay, then we keep track of the previous element. So it's like when we go to 1, okay, so let's say if I have I'll just show some code example. So let's say if I'll just do something like this, in theory so I'll have a previous, then I'll just say it's array. I'll do is I will increment. I will not increment. I will just assign it to the previous, what's called previous equals to array I. So this is one way just taking the previous. We keep track of the previous element so that when we meet it, then we know. So if we meet it, if like the current element equals to the previous element, then we know, okay, we have a duplicate here. So then we remove this element. So this is what we'll do. Like if we are dealing with arrays. So asking any question. Oh, okay. Okay, so then we'll remove this element. So this is how we'll do it in array. But can we do this in linked list? Yes, we actually can. We can keep track of the previous element and then we compare and then we just remove. But this solution is where we try to think linked list as an array and then use an algorithm that works for array and make it into a linked list solution. This is a viable solution. It can be done, but today I'm going to introduce another solution, which is I think this is the most efficient that I can think of to solve this question. It's because that it behaves like a linked list, so we can do this. For normal arrays, we're not able to do this. What we can do is here, we're going to we are able to we have like a pointer. So when we talk about linked list, you always heard about like pointer. It's because that is how we traverse through the linked list. So when I meet the first element, right? So this is my first pointer. So when I'm at the first element, what I can do is I can actually check the next element, because if you look at the implementation of linked list, you actually have a pointer to the next element, so you can check, so you can see the next element what it is. So at the first position itself, I can already know, okay, is it that my next element equals to the first element that I have. So if the next element is equals to the current element, then what I can do is I can replace the second element with the third element. So it will be like this. So if I meet the same element, okay, so what I can do is I will just remove it's not technically remove. I replace this with this, and then the behind one is removed. Then I will have like a completed linked list where I don't have any duplicates anymore. So let's just try with like a bigger another input So if I have this, yeah, if I have like 1 1 2 3 3, so at first I start at this position, the 0 position. Then I check with the next element, so they are equal, right? So because they are equal, I replace the next element with the next element. So I replace the next element with the next, which is 2. So because of how linked lists work out, even if I replace it wouldn't end up like this. It wouldn't end up like because like not in normal arrays, if you replace one value with the subsequent value, you end up with something like this. Then the value still exists. But because it's a linked list, if you replace the next value to be a next value, basically you're actually cutting it out. Basically you're cutting it out from the linked list. So this is this is why this solution can work only for linked list. If you consider that how this next element works. So this is only applicable for linked list. So this is at the first iteration. So at the second iteration, I'll reach here, and then I check whether the current and the next is equal. In this case, it's not equal, so I'll just continue. And then I check whether at this position, whether the current and the next is same. Okay, yeah, so I see, okay, the current and the next is same. So what I'll do is I'll replace the next element with the next element. So here you have some questions. Okay, how do I replace the next element with next element? Because the next element is empty. There's nothing there, right? Like normally in array, if you try to do that, it will always give you some error. It will give you error like error array index out of bounds something. This is a very famous Java error lah. But in other programming languages, it will give you error as well, because after this element, we don't have a next element. It's out of the array. We don't have that thing in the array. But in a linked list, because of how it works, if I don't represent it in like an array way, normally linked list appears like this. So it will be like 1, 1, 2, 3, 3. So it's connecting something. So the 1 is connecting to 1, connecting to 2, connecting to 3. And then there's actually the last one, the ending one. It will always connect it to null. Okay, and then the thing before will always connect it to null. Because null means like empty. It's like empty space in programming. So that's why it's always connected to null. At the back and in the front, it's also always connected to null. So that's why when we do like just now the middle linked list, there's a while loop, right? We always check whether the current pointer is at null, because we know that null is the end. Null is always will be the end. So basically if that's the case, right? So come back here. If we say the next element is going to be replaced with the next element, so at current position here, the next element will be 3. So this will be replaced with the next element, which is now. So if we to represent it, this will be something like this now. But because it's empty space, like we can treat like null as empty, so we are going to just ignore it. So it will just be 1, 2, 3. So basically, this is the solution of how we're going to do it. It's actually much more efficient because it's not always O of n. Okay, because like if we talk about like the time complexity lah, for the first solution, it will always be O of n. Because why? Because you have to create a set, right? You have to create a set. So in order to create a set, you always have to look through every element, then put them into a set. So you always have to look through every element in the array, which is O of n. Then for the space complexity, you always have something, because you have to allocate memory for set, and then you have to allocate memory for the thing that you'll be creating again. So it'll be all of like it will be all of like 2n, because like there's like two things, but like in the big O notation, we always like ignore the coefficient, so we can just say O of n and O of n. And for the second one, it is also O of n. Why? Because we're going to like iterate through the array, like always lah. We'll always look through the array until the end. So we are doing this amount of work every time. So like if there's like 1, 1, 2, 2, 3, 3, we're going to iterate here 1, 2, 3, 4, 5 times. And for the space complexity is a bit better lah, because we only keep track of one element, which is just one O of 1. We're not keeping like an array or something. But for this third solution, the time complexity will be, in the worst case, it will be O of n, worst case. But on the average case, it will be lesser than O of n. It will be lesser than O of n in the average case. We can't predict how much but on an average case, will be lesser than O of n. Why I say so is because let's say we have like 1, 1, 2, 3, 3, right? So in the worst possible case we were going to like iterate through all of them like maybe 4 times not 5 times but 4 times. But in average case because when you see the whole thing, right, even though we have like 5 elements, but when we are at the first iteration, we are not going to traverse this element. We are not going to traverse this element that is going to be replaced. Because it's going to be replaced, we didn't traverse it. So in this case, although there's 5 elements in the linked list, but we only make like 3 travels. So I mean we only go through like 3 elements. So it's always like unless your input is like there's every one of them is duplicate, something like, unless your input is something like this, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. Then probably you have to go through O of n time. But if it's not always having duplicate, then this is a much more efficient solution, because you don't do the extra work. In all these like the previous like algorithm, you're going to do extra work, because even though it is even though if it's like a duplicated element, you're going to still look through. So it's always guaranteed that you'll be O of n. So that's why it's a much better solution in terms of time, and also for the space complexity. It actually doesn't use any extra space, so it's also O of 1. It doesn't use any extra space because you didn't allocate space for anything. So yeah, so this is the algorithm that we're going to implement for this solution, for this question, for this problem. Is it clear so far? If it's clear, then I'll just like go through the implementation. Yeah, Discord don't have emoji. If it's if it's clear, then you can just like, I don't know, react with some emoji or something. Eh, yeah. So do the job. Yeah, so let's implement it. So today I'm going to do a little bit something special. Is where it's something quite frustrates me lah. But I'm going to solve this. I'm not sure whether you all have this kind of problem when you do Leetcode, right? And you try to run the code very quickly, and then it will just like of course it doesn't work now lah. So because I'm not returning anything. So like when you run Leetcode for a lot of time, like you keep spamming the button, it'll say that we have to wait because we're not using like premium account or something. So if I keep running it a lot of time lah, it will say like something. So and also it's quite hard to debug lah, I find it, because sometimes it doesn't give you like the standard output thing. So today we're going to do something different. We are still going to solve this problem, but I'm going to solve it in my own editor, where I wrote a few functions to help me run the test case, so I can specify my own test case, and also some other stuff. So let me just zoom this in because I think it's quite small on screen. But basically what we're implementing is just this function. This thing is provided by Leetcode, where it tells us this is the definition for the singly linked list, and this is the function that we want to implement. So it's remove duplicate from sorted list. So this is the function that we want to implement. Or delete duplicates. Basically the same now. It's just that we write it on our like local IDE so that we can run as many times as we want, and also we can do other custom thing. So basically well, this is the solution. So let's not like just give the solution like this. Let's just go through it. Let me just do it together with you. So first thing first, when we deal with linked list, they will always give us like a head element. So this head element basically it's this one, okay, the head. So this in this whole linked list, the one is the head. So they will only give us the head, which is one in this case. We have to traverse it ourselves. Like we have to do .next until the end. So if we were to do something like this, because we have to traverse, right? So if we do something like head then head.next, then we'll have a problem, because we'll never get back to the first element, because we traverse it until the end. We are not able to like access to the first element. So always we have to make a copy. Some people call it a domino, some people call it a copy. I don't know, I just call it a copy lah. So we always have to keep a copy of like the first element. So what I'll do is I'll do like current. I'll assign like a current pointer every time lah. So this cur means like a current lah. It's basically this thing lah, this pointer that we always have when we want to deal with linked list. So I will just use that cur as the current, so that the head doesn't move. So what we'll do is like I mentioned. So what we'll do is we'll traverse through the linked list, and we'll traverse through the linked list. Then we check whether the current element is equals to the next element. So if it's equal, then we remove or we replace it with the next element. That's what we'll do. So let's just do this. So in a while loop, we need to have like a exit condition, right? So this exit condition is exit when pointing at null. Okay, this is what it does, because we say the cur cannot be equal to null pointer, which is we will exit the loop when it is null. So what it means is where if we were to iterate through the linked list, so here it's okay, here okay, here okay, go on until finally we'll reach this null. So if it's null, then we'll just exit lor. So but in C++ it's quite special lah. You can say null is NULL capital, you can say null PTR. They mean the same thing. So so this is our exit condition, because when we reach the end we want to exit. else the program will just keep on looping. Because if you do not know, because actually our linked list never ends on. It actually been chained in like a lot of now, but it's okay. That's why we have to deal with this exit condition. So yeah, so this is our exit condition. So what we'll check is we'll check whether the current value equals to the next value. So this is what we'll check. Okay. If they are equal, then we'll have to do something. So in order to like make sure it's not also have to check like whether the next is not null pointer. So because we're comparing current x, okay. So if current x is null, right, and then we try to access the value of current x, there will be an error. That's why we need to have this check in place, where it's the next like the next value must not be a null pointer as well. This is where the case is in like when we are reaching this last element, then we would want to compare because we would want to compare with null because we know already the last one must be null and then they must not be equal. So we just skip this. We don't want to check if it's null. If the next is null, we just don't want to check. So that's what we do. So this is the we want to check if I check next element is not null. And current element is equals to next element. Wrote the code for this. Oh, great! It's really great. Okay, so let me finish my solution first. I'll check back that. I'll check back that in a moment. So basically, this is the condition that we want to check. Then what we'll do is, if we meet like so let's say we are at 1, right? If we are at 1, then we check that the current element and the next element are the same. So we basically want to replace this one element with the next element, which is 2. So basically we just like can say we remove it lah. So what we'll do is we can just say cur next if it is equal is equals to cur next. This is how we it's basically saying that this position should be 2. So I'll just like remove it. So this is basically what it does like in this block of code. And other than that, we'll have to like keep on incrementing. So we'll just say cur next is equals to we'll just say cur is equals to cur next. And so this is how we like go through the whole linked list, like from here to here, because we have to point this pointer at the next element, then we point this pointer at the next element, because remember that curr, C-U-R-R, this is our current pointer that we declared it to be. So in the end, we just want to return head, because it wants us to return the whole linked list. If you see 112, they want us to return the 12, and we know that it is the head because by the return type is a pointer, is a reference to a list node, so it always wants us to like return the first element in the linked list. But there's one potential problem here. If we use if, what if our linked list looks like this: 1 1 1 2 let's just check if we're going to have this, is this going to work? And basically I've already created I've written the test, the test. It doesn't look nice lah, but I've written the test case, so we can just run it and see if it passes. If we're using this implementation, if it passes the check lah. So no worry, all this code will be published on GitHub later. So if you need to see how you can write the test case, or you want to see like how all these things are done, you can check it later. So so let's just test this. Speed as well. So it actually passes. So yeah, it actually works like if we use if, because there's another way. If we don't want to use if, we can also use while. Okay. But I think both works as well. That both also work. The difference between while and if is if we are using if, it will just check this for one time. If we are using while, it will like keep on checking and keep on checking. I think both like they're the similar lah, because we will look through the whole thing somehow. So I think they're similar. So this is the implementation that I had. What it will do. So you can just comment this. We say, move to next element. So this is what it does. So this is the whole implementation of it. I can just copy this, put it to here. Okay. Okay. So let's just run the test case. It should work. Okay, it works, and we run the second test case. Yep, it works again. So we can submit this, and this should probably work. No, it doesn't work. Okay, so let's see. Input 111, and then the output is 11. Okay, so it's just okay. It actually doesn't work. So if we put it back, so I can create like a new test case. Maybe I make this smaller so it's so the test case here I have is like 112 input, and it should return 12. Then I have like 11233. It should return 123. So this is the case that it is failing. So let's just create a test case here. If it's 1, then it should return 1 only. That's how it's supposed to, because it says when we input 111, it should actually return just 1, not 2 1, because we have to remove all duplicate. So let's just test this. I think this doesn't work. You can see that it doesn't work. Like in the first test it passed, the second test it passed, but the third test doesn't pass. Where the third test is this case, where we have like a, maybe I'll just leave like a comment. So this is like 1 1 1, and then we have it to be 1. So this is like this is like 1 1 2, and then we expect it to be 1 and 2. So I can just put this here 1 2 3 3, and then create 2 and 3. Could be too small if I don't zoom them. But basically, this is the test case that is failing. So what we have to do is we just have to change this if to we have to change this if to while. So what does this while does is where it will keep on looping until it replaces all the duplicates, because there can be like 3 times, like 4 5 times like of the same element. So let's just test this out. If we were to use while, yeah, then the test case pass also. So this is the so basically this is like, if you don't understand what this part is, it's okay, because basically what it does is just a testing function that tests. It just feeds some input to the function that we wrote and then test it. So this is for some performance things. Basically this is the solution now, because like later on when we move on to like medium question or like hard question, it's quite important that we test our solution. Like in real life it's quite important that we test our solution. Is where in the medium or hard problem, it always requires us to like give it has like a time constraint, where if we go back to the description, I think it doesn't say here, but in some question, we must done it within 1 second. Like our algorithm must complete the thing in 1 second. So, but in like very large like programs or very complex algorithm, sometimes the code that we wrote is not efficient. So like if we were to use this algorithm, it probably may take more than 1 second. But in this algorithm, because it's faster, then it takes lesser than 1 second. So how do we know it's faster than 1 second or lesser than 1 second? The way that we test is like we can write our own test, because like I don't think Leetcode tells us yeah, it actually tells us. But when your solution is like really really slow, it actually doesn't tell you. It just tell you like I can give you like an example here. If you just do this, it wouldn't the error it would give me is just time limit exceeded. Is it? It give me wrong answer. Yeah, but that's what I try to say lah. It's like the testing thing maybe it doesn't make too much sense now, but if you want to test your algorithm and see how far it can go, the capability, the thing that you want to test, it's quite important to write tests. Even in like real world, when you go out to like write algorithms, it's quite important to write tests. So basically, this is the solution to this problem lah. Is there any question? Else, I'm going to look at Proton's answer. Yeah, if you have any questions, just put it in the chat or you can open mic and ask lah. So meanwhile, let's just look at the Proton solution. I'll just put this in my ID lah, so it's okay. So you have like this is your function. So it's called root for you lah. It doesn't matter like it's the same thing. So this head is where now this head is the like the current pointer. But I normally call this I don't call this head lah, cause this will increment and this wouldn't be head anymore. So depends on you lah. It's just naming stuff. So this one line. So okay, so if head is if head is null, like if not head lah, it's actually this check is equivalent to writing this. Actually equivalent to writing this like if head equals null. It's actually the same thing, but yeah. Need to keep it this way. So you check whether when the next is not null, okay? When the next is not null, if the value of the current value is equals to the next value, we'll just set the next to next. Yeah, it's basically the same lah. Else you just increment. Else you increment. This work this how we supposed to increment at each iteration, even though it is like something else like we're supposed to increment. But let's just test first since we can test it locally, so why not? Change this to root. It works as well. Okay, yeah. So I think this case is also works. So yeah, there's no problem as it works. I think it's because it works. It's because we already like incremented it like when we have like a next thing. So I think it's quite fine. Yeah. So this solution works as well. It's basically the same lah. It's basically the same. The logic is the same. When we meet like the current element is equal to the next element, then we'll replace the next element with the next element. So the algorithm is the same like essentially. It's just the code is a bit different, but that's fine. Yeah. So is there any question more like to this solution? Is it clear? Is it not clear? Or you have something to ask? All these solution will be posted to the GitHub later on. I'm not sure whether if you have, do they all have like the GitHub link? I can't find it, but I think they will have on Pine's comment. Or pin comment, okay. Okay, yeah. So yeah, if you want to look at the solution, it will all be here lah. Everything is posted from this is the week 1 solution. Oh, someone added the Java solution as well. Okay, it's quite good. So basically, this is it. Is there any question? If there's no, then I think that's all for today lah. Yeah. Do you have anything to say, Missing or Sammy or anyone? Okay, I saw someone typing.